All right, look up here for a sec. So let's do the homework quiz. So NO3, this is called nitrate. NO3 1 minus. So it turns out you can actually draw a couple of different structures for this one. So the first one looks something like this. We make a double bond and two single bonds. And these oxygens will be negatively charged. They'll have enough electrons to make them obey the octet rule, and they'll be negatively charged. This oxygen with the double bond only has 2 pairs of lone electrons. So this is the structure, but what about nitrogen? What's its formal charge right now? Is it formally positive, formally negative? How many electrons does it own? 4, right? So right now it's actually formally positive. What's the net charge on this molecule right now? I've got 2 negative charges. -1, right? And that's what you see in the formula here. In the formula here, you see a -1, and that's what this net charge is. All right?
I totally messed up.
Is that okay? So the other structures that you can draw are actually pretty simple. All you're doing is writing the double bond in different spots. So for example, I could write the double bond on this side, and I could also write it on the other side, right?
So
write it down here.
So that like line connecting nitrogen and like the 2 oxygens that go on the double bond, since it has like -1 in the thing, instead of 6 it'll have 7.
Exactly.
Is that why it has
Yep.
the thing?
Yep.
But if it stayed with 6, then what would you do?
So if it's 6, if oxygen owns 6 electrons, like take a look right here, okay? Right here, this oxygen owns, let me do it in a different color. So it owns 1, 2, 3, 4, 5, 6 electrons. And that's in its ground state, so we don't put any charge, we just put 0.
And then the line equals 2, and then
Each line equals 2 when you're counting the octet rule, that's how many electrons it owns and it's sharing, right? So it's not only how many electrons does it own, but how many is it sharing total. So in most of the time, it's going to want to look like neon, so it should have 8, right? Except for hydrogen. Hydrogen wants to look like helium, and helium only has 2 electrons. So that's how many you see around hydrogen most often after bonding, right? Does that all make sense for the homework? Okay. So I want to talk about how this relates, how Lewis structures can relate to real life. Does anybody know what a protein is? What's a protein made up of? Anybody know?
5 atoms.
Amino acids. Somebody said? Amino acids. So this is what an amino acid looks like. This is its structure. So you have a carbon bonded to a carboxylic acid. And then you have, on the other side, an amine group. And an amine group has 2 hydrogens like that. All right? So this is an amino acid. There's a functional group down here. They just usually symbolize it as R because it changes. You can attach all sorts of really complicated stuff to this section of the molecule. And you might be thinking to yourself, that central carbon should have 4 bonds, and it does. It has a little hydrogen right here. Okay? But there's this functional group, this R group, that can change. That's what makes up all the different amino acids that are possible. Okay? This R group changes. But when they react, see, this is why the Lewis structure is important, because it tells me a lot about its reactivity, how it should react. Take a look at this carbon right here. Should this carbon be partially positive or partially negative?
Partially positive.
Why? Why partially negative? Why partially positive? Think about what it's bonded to. Is oxygen electronegative?
I mean, yes.
It is. It is very electronegative. So when something's bound to an electronegative atom, what happens to the sharing? Is it equal sharing? It's unequal sharing, right? Oxygen is going to hog those electrons, and you're going to end up with a partially positive carbon here. And that's really important to understand. This is a polar covalent bond between carbon and oxygen. So carbon is going to become partially positive. Why do you think that's so important? It's going to tell us how it's going to bond. So look, what if I did this? If I put another one of these guys on the page, okay? Let's do this. Copy. Paste. Try it again. Try it again. There we go. Okay. So, sorry about that. I had to do some surgery. So this nitrogen right here, this nitrogen turns out has a lone pair. What do we know about nitrogen's electronegativity? High or low? High. Top right of the periodic table, right? Fluorine's the highest. Nitrogen's pretty close, right? It's really electronegative. And it's going to go out and grab this nucleus. This lone pair is going to grab that nucleus because it's positive. It's staring nitrogen in the face as a very attractive nucleus right now, right? It's partially positive, and nitrogen's electrons want to be attracted to positive things, right? Because they're opposite charges, and that's electromagnetism, right? Opposite charges attract. So this bond is going to form, but once that bond forms, right, this carbon is going to violate the octet rule. Right now it has 1, 2, 3, 4 bonds. That's 4 bonds right now. If we made an extra bond, it would violate the octet rule. So what's going to happen? Something's going to leave, right? Some bond is going to go away. It's going to be this one. This OH is going to leave as water, actually. So it's going to leave as OH, but there's always some H plus in solution that's going to come together as water. So this is called a condensation reaction because you produce water. This is the bond, this is the reaction that happens to connect amino acids together and make proteins. It's also the same reaction takes place, the same type of reaction, takes place to bond your DNA together. How many diseases are related to amino acid structure? Do you think?
More than one.
46 well-known proteopathies. Okay? There are 46 well-known proteopathies, diseases related to the forming of a protein. How many genetic diseases are there? There's over 6,000 well-known genetic diseases, all related to the formation of these bonds right here. Right? So if you understand this chemistry, you're a step closer to getting your foot in the door medicine-wise, right? If you want to be a nurse, a PA, a doctor, right? So that's how this connects. And it turns out there's a whole lot of other applications, right? From being an actual chemist, right? Building polymers, building drugs, right? To treat disease. Being an engineer, doing chemical engineering. There's a lot of connections here. So this is really important. We're working on our problem sets, and in addition right now, I want you as groups to build one molecule, all right? So here's a molecular model. You guys are going to build perchlorate, that's ClO4. You guys are going to build sulfate, okay? That's SO4. Okay? You guys are going to build sulfite. Sulfite. That's SO3. You guys are going to build chlorate, ClO3.
What was the actual name of it? CLO. Because I know it's CLO4.
Perchlorate.
So,
And you guys are going to build chlorite. Chlorite, ClO2.